shoot. My screen's not working anymore. Okay. It's okay again.
Manuel, hi.
Hi.
Hi, how are you?
Okay. Do you still have blue sky out of the window, or is it a fake photo?
It's a fake, but it's my office.
Should be even later than in China, right?
It's 9 o'clock. It's 9 o'clock here.
2 p.m. here.
Oh.
It's daylight, but gray.
No, I think it's time to start our evening session for now. And our first speaker will be Manuel Jess. He will talk about dark matter mediators at colliders. So let's welcome Professor Jess. Please go ahead.
Thank you. Yeah, I was tasked to talk about dark matter at colliders, but as we will see, mostly what you can test is actually or look for at colliders is the mediator that mediates interactions between dark matter particles and standard model particles. So I'll start by briefly reviewing the argument why one thinks there might be couplings between standard model particles and dark matter particles. Then I'll give a bunch of caveats to that argument. And I'll very briefly discuss the production of dark matter particles by an off-shell mediator. In fact, that is usually not very promising. And then I'll discuss production of mediators, which can be promising in many cases, before summarizing. So here I will focus on thermal dark matter, because otherwise usually there are no collider tests. Thermal dark matter are dark matter particles denoted by chi here, which have been in thermal equilibrium with the standard model. That's my definition of thermal dark matter, which means that the interaction rate turning chi particles into standard model particles must have been bigger than the Hubble rate at some point. Okay, and that requires for temperatures larger than the chi mass, and assuming for the simplicity that the mediator mass is of the same order of the chi mass, that the product of the annihilation cross-section times number density must have been higher than the Hubble parameter, which is of order t squared over m Planck, and this product is of order coupling squared times t. Therefore, you need the coupling to be bigger than root t over m Planck parametrically. And that's easiest at the lowest temperature, which here is t equal of order of m chi, because remember we assumed that t is bigger than m chi. So that is a pretty small coupling. So it's not difficult to satisfy this criterion in a given model. Okay, if this is true, then chi will decouple at temperatures below m chi, because then the number density becomes exponentially suppressed, which means it forms cold dark matter, which is good, because that's what simulations tell us that we need to describe structure in the universe. And as you have probably, most of you have seen, this calculation gives a relic density of the desired order of magnitude for an annihilation cross-section of the order of a picobarn. Very nice. Okay, that means, again, assuming that the mediator mass is similar to the mass of the dark matter particle, you want to have a coupling of the order of, say, 5 times 10 to minus 5 alpha times dark matter mass over a GeV. That's, of course, a very rough estimate. But it tells you that this can be in striking range of collider experiments. If you put a few hundred GeV, for example, on the right-hand side, you get a typical V coupling on the left-hand side. Okay, there are, of course, caveats for this argument. First of all, I assume dark matter was thermal. So I'm assuming thermal dark matter production. That does not apply for a bunch of dark matter models that have been suggested. Even there are thermal models for which it doesn't work, in particular for these so-called cannibal models, where the freeze out happens through number changing reactions within the dark sector. Also, really the quantity of interest here, of relevance, is the annihilation cross-section for dark matter particles into anything else. And this anything else here, of course, need not include your favorite beam particles. The particles that we can accelerate is basically electrons, light quarks, and gluons. And if anything else, if it's not a standard model particle at all, but some new singlet particle, for instance, then you're basically out of luck as far as collider tests are concerned. Anything else may also be dominated by heavier standard model particles, in which case we will need higher order processes to probe this sector. For example, if you have a dominant coupling to top quarks, then you could look for processes like top production plus dark matter, or if it's for second generation leptons, you look for muon pair production plus the mediator, or something like that. But you will have to go look at higher order processes. Also, even within just ordinary thermal dark matter, it's still quite possible that the dark matter mass is above a TeV. In this case, we are again out of luck as far as collider tests are concerned, because our current colliders cannot probe this, basically. Because somebody at some point may build a 100 TeV PP collider, then the situation will be different, but until this happens, we are out of luck. So there are, unfortunately, quite a large number of both thermal and non-thermal dark matter models that cannot be tested at colliders at all. Final caveat, if your dark matter particle has a mass above 10 GeV or so, or of the order of 10 GeV or more, and if it has significant scalar or vector couplings to light quarks, U and D quarks, then there are very strong constraints on these couplings from direct spin-independent searches for dark matter. And these constraints are much stronger than what you can probe at LHC, so that's not a good scenario. If these couplings are axial vector, then you have to resort to spin-dependent couplings, spin-dependent dark matter search. The constraints are significantly weaker, but still you get a quite sizable upper bound on the coupling in this case, which you have to obey, of course. Okay, now let's briefly look at dark matter production via off-shell mediators. And I would argue that at the LHC, this is basically hopeless. First of all, just pair production of dark matter particles is invisible. You just have two invisible particles, so that's not a signal. You have to emit an additional detectable particle, a jet or a photon or whatever, that goes under the name of mono-X, such as X is this additional particle. So that means it's, again, a higher order process which has a reduced cross-section. So the signature is then this X production plus missing ET, but because we're talking about off-shell mediators, this is a 2 to 3 process. Okay, and the bad thing is that the leading background comes from 2 to 2 reaction, namely the same X produced together with a Z boson with a Z decaying into neutrinos. That's also missing ET, of course. And the couplings are usually unsuppressed here. So you're comparing the 2 to 3 new physics reaction with a 2 to 2 background, and in fact, there are even additional backgrounds. As a result, the systematic error on the background is typically of the order of the signal or even larger, as has been shown, for example, in this paper a number of years ago. So that means you can't see it. At the plus and minus colliders, the situation is a bit less bad, or might be better at least. Here, of course, the basic argument that you have to emit something in the final state to make it visible is still true. The simplest thing you can emit is a photon. And also here you have a 2 to 2 background, plus and minus into Z plus gamma, with Z again decaying invisibly. However, because now your center of mass energy is fixed, it means that the energy of the gamma in the final state is fixed and can be then removed, these events. Okay, what's left then for the background also comes from 2 to 3 processes, background processes, which you can compare with your 2 to 3 signal process. And the energy spectrum of the photon is usually different. So that gives you a fighting chance at least to look for this and find a signal. Of course, there are some caveats too. This will only work if your mediator couples to electrons, because that's your beam particles. And also remember this order of magnitude estimate of the coupling. The coupling you're aiming for is actually very small if the dark matter mass is small. So this kind of search will generically work better if the dark matter mass is not too far below the kinematic reach, if at least the estimate is correct. Okay, so just producing dark matter particles by an off-shell mediator is not very promising, and certainly not for the LHC. So let's look at the production of the mediators then. So here, mediator means for me the particle that mediates this annihilation of two dark matter particles into anything else. And as already said, if anything else is not part of the dark matter, then we're usually out of luck. So here I'm focusing on the situation where this anything else is mostly standard model particles. Okay, that an S-channel mediator is an S-channel in this process, so it couples to two dark matter particles and also to standard model particles in order to mediate this. Whereas a T-channel mediator will couple, M is the mediator here, couple one dark matter particle to one standard model particle. There's one important difference, or several differences. One important difference at this point already is that the S-channel mediator can have any mass, can be lighter or heavier than the dark matter particle, whereas a T-channel mediator must be heavier than the dark matter particle. Otherwise, the same coupling would allow the dark matter particle to decay. And then it's not dark matter anymore, obviously. So now let's consider what happens if your dark matter particle is not a standard model singlet. That might look nice, but actually it isn't. Because at least in standard cosmology, you need a mass at a TeV or more, often considerably more, depending on what exactly your dark matter particle is. Plus, you don't need any new mediators in this case. They're just annihilating into pairs of W and Z bosons, and those, of course, you already know, and they don't tell you, as such, don't tell you anything about dark matter. So in particular, these minimal dark matter models where you have like a triplet or a quintuplet or something of dark matter particles with multi-TeV masses, that's not really testable at near future colliders again. There's one exception, and that's Higgsino-like neutralino and SUSY. Again, finding the Higgsino will be basically impossible at the LHC, but you have done lots of other superparticles, of course. They don't play much of a role in the prediction of the relic density, but they should still be there. However, even then, the situation is not really that promising. After all, your lighter superparticle already has to have a TeV mass in this case. And if you have gauge mass unification, for example, they will tell you that the gluino mass and also the squark masses must then be above 4 or 5 TeV beyond LHC reach. So it's better actually if a dark matter particle is a singlet under the standard model gauge group. Now, for T-channel mediators, that means that they should have the same gauge quantum numbers as the standard model particles in the final state. If you have chi to FF bar, in particular, there should be a scalar with the standard model quantum numbers that behaves pretty much like a fermion. And here, it would behave like a Higgsino for fermionic chi. Okay, so that's what I said. Chi annihilation into FF bar via scalar. This is like a fermion. Here, chi for fermionic chi. And the mediator would also have to be fermion with like a Higgsino, which you can look for them. And this argument is in fact very similar. Also, if your chi is spin 0, then the mediator here would have to be a fermion also, but still it has to couple to a standard model fermion plus your dark matter particle. So the spectral-like heavy fermion can be searched for with very similar methods as these fermions in SUSY. So yes, spectorially, chi fermion chi going to a fermion F, then the mediator would have to be a scalar and carry same quantum numbers here. Opposite way, if this chi is scalar, then the mediator would have to be a fermion, like a vector-like fermion, again with the same quantum numbers there, can be searched for by a pair production at the LHC. Right? So it's a nice situation. And in this context, in particular, the mono-X searches, which I before said are quite useless for direct dark matter search via off-shell mediator, they can become useful if the mass difference between the mediator and the dark matter particle is small. Remember, the mediator has to be heavier, but it doesn't have to be a lot heavier. So that goes under the name of compressed spectrum searches and supersymmetry. And there, these mono-X searches are useful to fill some corners of parameter space. So in a reminder of the talk, I will talk about singlet dark matter particle annihilating via an S-channel mediator, which then also must be a singlet because it couples to two singlets after all. Now, remember, before it should not have sizable couplings to U and D quarks from the direct dark matter search. So the standard Z prime type searches do not apply here. So again, at LHC, we'll have to look for some higher order processes. Nevertheless, the mediator can still decay into two standard model particles. So we can look for an invariant mass bump, however, in a multi-particle final state. Or, of course, the mediator can decay into dark matter particles invisibly, in which case, again, this mono-X searches will apply. So a brief remark on the decays of the mediator. For an on-shell mediator, in principle, you cannot distinguish on an event-by-event basis between invisible decays of mediator into dark matter and invisible decays of mediator into neutrinos. So you don't know whether you have found dark matter or neutrinos. However, if the mediator mass is larger than 2 times the mass of the charged lepton, which isn't very heavy after all, then from gauge invariance, the branching ratio for mediator decay into SO2 doublet charged leptons will be basically the same as that for decay into the corresponding neutrinos, as per SO2 gauge invariance. So by looking for this mediator to charged lepton decays, you can tell whether or not the mediator can decay into neutrinos. And if it doesn't, and you still find invisible mediator decays, then you can be pretty sure that this must be dark matter. Also, if the mediator is indeed a pure standard model singlet, then a renormalizable coupling to Fermi and anti-Fermi pairs in the standard model is only possible if it has spin 1. So it's a new gauge boson, basically. A scalar singlet can decay renormalizably only through coupling to H squared, to standard model Higgs bosons. Then it can decay into FF bar via mixing with the standard model Higgs, or it can decay into 2 pairs of Higgs bosons. So from the rest of this talk, I will focus on the simpler situation where the M is a new gauge boson or new spin 1 particle. The first example I want to briefly mention is a mediator coupling to heavy quarks. Again, couplings to light quarks would be very strongly constrained by direct dark matter searches. If it is a vector coupling, then only U and D coupling must be forbidden. So we assumed equal coupling to all other quarks. I should mention that this is work I did with Songwei Chang a couple of years ago in a couple of papers. For axial vector couplings, you should forbid also couplings to the strange quark because the spin-dependent interaction is also spin-dependent dark matter search is also sensitive to that. So we only allowed couplings to third generation in this case, again, taking them equal. And also for axial vector couplings, you have to respect the unitarity bound that has been pointed out by Carlo Fadal in 2015. And we recast then Atlas searches at that time only for 36-1 inverse for jets plus missing ET and for BB bar resonances using this checkmate code. And here's the result. These constraints up here, they are what you get from recasting older lab results. They're not terribly exciting. At the LHC, if you have a sizable branching ratio of the mediator into dark matter particles, then the bound of the coupling can go down, of the squared coupling times branching ratio can go down to the order 10 to minus 3. For larger mediator masses above half a TeV or so, there is also a search for BB bar resonances. However, in this case, the invisible decay, this dashed curve, in fact, still gives the better bound than the visible decay. That's somewhat unusual. Most of the time, the visible decay of the mediators gives the tightest constraint. But again, this only works, visible decay anyhow, currently only works, at that time, I should say, only worked for mediator masses above 600 TeV. So you see that for if the branching ratios are comparable, at least the invisible decays give better sensitivity. Second example I want to briefly mention is the extension of the standard model by the gauge group, where you gauge the difference between muon and tau lepton number. So it has been pointed out 30 years ago that this is an anomaly-free extension of the standard model without having to introduce any additional fermions. Of course, you don't have any coupling to electrons, at least not at tree level, so you don't get any serious bounds from lab here. You can also use the symmetry to constrain neutrino masses, and you can get realistic results out of that. You can accommodate a thermal dark matter particle in this framework. Of course, you have to assume, if you want to use this gauge boson as a mediator, you have to assume that the dark matter particle does carry a charge under this new gauge group. So it must carry a mu minus L tau charge. And this model has become topical recently, again, because it can explain the G mu minus 2 difference, as has been pointed out 15 years ago, almost. So again, with Chongyi Zhang and Meng Shi, we looked at LHC constraints, recasting a large number of multi-lepton searches. One typical production diagram is shown here. Again, this thing mediator couples only to second generation and third generation leptons. So you have to produce it at LHC via this kind of higher order processes. Here a charge current reaction, but that tells you also that you get several muons in the final state. And one of them has an invariant mass pump, but no search for this kind of search final state existed except one CMS search. We'll come to that in a minute. So here's the result of this recasting of the bounds. First of all, this brown region is what you want to explain the G minus 2, G mu minus 2. Then the blue solid line is the recast of the 4-muon constraint. And here in this region, there is actually a CMS search for Z to 4-muon decay, which was optimized for this with this kind of model in mind. So here you get very strong constraints. Outside of this mass range, however, especially for mediator masses above the Z mass, the 3-lepton constraint, which is this red line here, is better than the 4-lepton constraint. However, also in this, again, outside of this region covered by the dedicated CMS search, the light blue dot dashed line, which is the trident search limit, is actually stronger than LHC limit, and it excludes the G nu minus 2 explanation, as you can see here. So the LHC constraints are still, or were at this point, still fairly weak, except for those that are covered by dedicated CMS search, but that only works for ZTK, so for mediators lighter than the Z boson. So there's certainly significant room for further improvement. The 3-muon searches would have better sensitivity because the charge current cross-section is bigger than the neutral current cross-section at sufficiently large invariant masses at the LHC. And again, this trident search, it was this light blue line, that already excludes the explanation of G mu minus 2 in this model for mediator masses above a GV or so. So let's look then at small mediator masses. That's some very recent work just put on the web with the student of mine, Wenbin Zhao. And here we pointed out that for a coupling around 5 times 10 to minus 5, that's now the gauge coupling, not alpha, mediator mass around 20 MeV, and the dark matter mass just slightly above half of the mediator mass, and can explain quite a lot of things simultaneously. You get right Rayleigh density for thermal dark matter, of course. You can explain G nu minus 2. For the small masses, this is in agreement with the trident bound. You can explain or relax at least the Hubble tension by increasing and effective the number of radiative degrees of freedom in the early universe, because this light mediators decoupled so late that some of the muon and tau neutrinos are produced after they in turn decoupled from the photon bath. You can even explain part of the flux of 511 keV photons. That's a very old puzzle, exists since the 1970s, that various satellites have found an excess flux of 511 keV photons, most likely from the annihilation of electron-positron annihilation at rest, of course. So this can be explained here via chi 2e plus or minus. That proceeds only at one loop because there the mediator mixes kinetically with photons via muon and tau loops. So in this case, we can in fact explain this excess if your mediator mass is sufficiently close to 2 times the dark matter mass. So here are various constraints. Here in this purple region, you have too much dark radiation, so that's excluded. In the gray region, CMB, the annihilation of the dark matter particle into muons is possible, that would dump too much energy into the CMB. That's excluded. The green region here is what you want to have for G mu minus 2. And here a bunch of other upper bounds. The dark green one, this one here, is for coherent neutrino scattering. And the CCFR, so the trident search, is this dark red one, this one here, which also limits the parameter space considerably. And in this light blue region, you make a significant contribution to relaxing the Hubble tension. At this benchmark point there, you can explain many things, as I said before. And there are some predictions. One curve that I didn't mention, this black one here, that comes from white dwarf cooling, so it's not too far away from the best fit point that we have there. So we do predict slightly higher cooling rate for white dwarfs, higher the emission of muon and tau neutrinos. That might have in fact been observed. It has been interpreted in this paper in terms of axion emission, but other additional cooling mechanisms would probably work as well. And there's even a slightly improved description of ice cube data has been argued in this recent paper, because the Weber composition will change from resonance scattering of these muon and tau neutrinos. We also predict in the full Bell 2 data set something like 250 photon plus nothing events. If somebody ever builds a super tau charm factory with a luminosity of 2 autobahn inverse a year, a similar number of such single photon events should be found there via this simple diagram here. Again, you see this kinetic mixing between our mediator and the photon via mu tau loops. And of course, this works only if you can actually trigger on this single photon, because that's the only visible final state, or visible particle in the final state. So here's my summary. Many thermal and non-thermal dark matter models cannot be tested at colliders. Usually we have to rely on on-shell production of mediators. However, plenty of unusual mediator production and decay chains still remain to be explored at the LHC. And this U1 mu minus L tau model can explain lots of things and can be tested at future colliders if they have a single photon trigger. Thank you.
Okay, thanks, Manu, for giving a really nice talk. So any questions from audience or comments? Yes. You can just unmute, right? Yes.
Okay, very good. Thanks a lot, Manu, for your talk. Nice to see you in Beijing. I assume that you are in this U1 LE minus L tau, you may also have other problems to constrain, like F's flavor change in neutral currents. Also, when you have gamma M mediator, you may have also Z M mediator. You have to play a little bit with the electroweak Copley correct observables and all that.
So there's very small couplings.
You have done all that stuff, but you did not have time. Can you comment on that? How they affect your analysis?
For our favorite point, the coupling is very, very tiny, remember. It's a 10 to minus 4 or even smaller than 10 to minus 4. And the mixing with the Z is then also, because of we have a mediator mass of 20 MeV, is very strongly suppressed. So that these effects are small. And you don't have...
But you have Z prime, which is quite heavy in your plot, right? You have a
before, yeah, okay. That's right. No, in this case, we did not consider that specifically. But again, the mixing is in the minimal case, the mixing is pretty small because it's only half produced via muon and tau loops, so it's not a big issue. And flavor change in neutral currents, I don't think you have, except in the neutrino sector, maybe, where they mix, but that you don't see. Well, you do know, of course, you have Weber oscillations in the neutrino sector.
Don't have, you give the quarks, the leptons, the Z prime different charts, and you know by one of my
yeah, of course.
Supervisor.
But you don't know whether there are any off-diagonal charge lepton Yukawa couplings, right? You don't know that. the mixing, the known neutrino mixing can all be in the neutrino sector. Therefore, then you don't have a problem.
Okay, I understand. Okay.
Okay, thanks. So I see one question in the chat. Can you see it?
Wishang models can be tested at colliders. Yeah, that's what I was trying to talk about. I don't want to give my talk again.
Okay, any other questions?
Many can, many cannot.
Okay, so if there's no question, let's thank Manu again for giving the very nice talk. And the next speaker is Ning Zhou from Shanghai Jiao Tong University. So
hi, I'm here.
hi. Yeah.
Let me share my screen.
Yeah, maybe Manu can just turn off the share screen and yeah.
How do I do that now?
I think it's in the middle of your screen. You can move your mouse there and they'll show up. Yeah, I can do it for you actually.
Yeah, that might be better.
Okay, yeah.
Thanks.
Okay. So
So you can see my slide now.
Yes. Professor Ninzo, you can just start. Go ahead.
Okay. Hi, everyone. First, let me thank the organizer for inviting me to report the progress and plan of PanX experiment. As we all know, dark matter is one of the known physics beyond the standard model. Searches for dark matter in the lab can be grouped into 3 categories: direct detection, indirect detection, and collider search. These 3 approaches provide complementary information to each other. The direct detection is searching for dark matter halo of the Milky Way, which scatters with the target atom and produces recoil signature in the detector. But the signal is quite weak and rare. Therefore, such detections is usually performed in an underground lab where cosmic ray flux is largely suppressed by the Earth above. So currently, there are several multi-ton scale direct detection experiments running or under construction in underground labs, including the LZ, SUSY20K, Xenon NT, and PanX 40. So in China, we have the deepest underground laboratory in the world, the China Jinping Underground Laboratory. It was built in the middle of a tunnel passing through the Jinping Mountain with 2,400 meters below the top of the mountain. So in the second phase of the Jinping Underground Laboratory, CJPL2, there are 8 new experiment halls, which have enough space for next generation direct detection experiments. So the B2 hall is for the PanX experiment. So the PanX collaboration formed in 2009 has 14 institutes and 70 members. So this experiment used the dual phase xenon time project chamber. So incoming dark matter scatter with the atom, deposit some energy in the detector. It can generate a scintillation light, which is called S1 signal, and ionize the electron signal, which converts later into a delayed light, S2 signal. So based on this S1 and S2, the detector has a precise energy and a 3-dimensional position reconstructions. In addition, the nuclear recoil events can be separated from the electron recoil events using the ratio of S1 and S2. So in the past 10 years, the Pentax has completed the two phases, the 120 kilogram and 580 kilogram liquid xenon experiments. So now is the Pentax 40 experiment on stage at the CJPL 2. So the Pentax 2 580 kilogram liquid xenon experiment finished running in 2019. So here let me show several recent results from the full exposure of Pentax 2. So the Euro dark matter search is looking for nuclear recoil signals, but some models like solar axions or neutrino magnetic moment that can produce electron recoil events. To understand the electron recoil spectrum in the data, precise shape of the major background is needed. So in this analysis, we obtained the corresponding spectrum for tritium, krypton, and radon directly from calibration data. So this analysis will also perform as an independent check of xenon 1 ton low energy electron recoil access. It turned out that there is no tension in our data if the access is real. So a new and more sensitive detector is needed in order to have a definite answer to this access. So another interesting search is also on the electron recoil events. So nuclear recoils due to the light WIMP particles are too weak to be detected. Instead, the electron recoil signals from this light dark matter are within the detector reach. So in this analysis, we require the S2 only signature. That means we only use the ionized electron information and release the requirement on the initial small scintillation light, so that the effective threshold can be reduced down to 80 electrovolts. Eventually, we obtained the world's strongest constraints for dark matter between 15 to 30 MeV. Okay, but for the other sub-GeV dark matter, that can be boosted by cosmic ray in order to have enough energy to scatter the nuclei. So that's also due to the same dark matter nuclear interaction. So when the dark matter reaches the underground laboratory, the Earth along its path can also interact with dark matter and suppress its flux and energy. Therefore, a diurnal modulation effect is predicted as shown in the top right figure, and it can be used as a new smoking gun for such boosted dark matter. So we performed this analysis using the data below the nuclear recoil median line. The 25 events are observed with expected 26.6 background events, and the constraint on the MeV level dark matter are showing in the bottom right figure. So this is preliminary results, and we will public send to the archive soon. So that's for the Pentax 2. In 2019, the Pentax 40 moved to CJPL 2, and the installation started. So in the hall, there is a big high purity water tank. So the detector is deployed in the center to screen the radioactivity in the lab itself. So the installation completed in 2020, followed by some testing and commissioning. So here are some pictures of the Pentax 40 subsystems, including the TPC, PMT, electronics, cryogenic system, there's a xenon storage and distillation tower. So the whole commissioning lasted 95 days, and the xenon purity, as indicated by this electron lifetime is increasing continuously through the xenon circulation and the purification system. So as compared with Pentax 2, there are several major improvements in Pentax 14. We adopted the trickless DIQ. So the average single photon detection efficiency is 96%. Now also the radon level is reduced by a factor of 6, and the krypton level is down by a factor of 20, which can guarantee the sensitivity of Pentax 14. So the energy reconstruction has a good linearity, which is based on the S1 and S2 signal. The resolution at 40 keV is around 6.8%. So that's measured in krypton 83 isomer calibration. So the detector response to electron recoil and nuclear recoils are derived from the radon source calibration and 2 types of neutron sources. And the model itself describes the data pretty well. And eventually the S1 and the S2 taken and selection efficiency are measured from data as well. And we can see that the overall efficiency plateaued at 80% as a function of the nuclear recoil energy. Okay, so based on the background simulation of the whole detector, we choose the best fiducial volume as 2.67 ton. So the region selection is showing in the right figure in the detector transverse plane. And during the commissioning, unfortunately, we identify the tritium spectrum showing this is one of the data the wrong period. So as a function of the energy, the spectrum can be fitted pretty well by the tritium. So the tritium is likely from a tritium calibration at the end of Pentax 2. The polluted xenon is then filled in a Pentax photon, so that the tritium level is fitted directly from data. And so here is a summary table of the background budget. So in total, the background is estimated to be about 1,037. So the dominant contribution, as can be seen from the table, are from the tritium and the radon. So below the nuclear recoil medium line, the expected background is around 10 events. But even though with the tritium, the overall background per unit target is still improved by 4 times as compared with Pentax 2 in the low energy region. So in the data, after the selection, that is the S1 between 2 and 135 PE, S2 smaller than 20,000 PE. So the photon, this is the unit of the photon electron, which corresponds to around 30 keV E. And there are 1,058 candidates, and with 6 events below the nuclear recoil medium line. So these candidates are uniformly distributed in the fiducial volume as shown in this plot, in the 2 plots on the left. And for the 6 events below the nuclear recoil medium line, the likelihood indicates that they are most likely from tritium and radon. Okay, and then the whole spectrum agrees well with the expected background. So the P level of the background only fit is 0.58. There is no significant excess observed. So from this 0.63 ton-year commissioning data, we obtained the constraint on the larger mass WIMP nuclear spin independent interaction, which is also the strongest in the world. And from this line, we can see that it has dived into previously unexplored territory. And also in the low energy region, it's approaching the so-called neutrino floor. Our next immediate plan is to remove the tritium through offline xenon distillation. And meanwhile, we are preparing multi-phase tasks, including the dark matter, xenon 136, neutrinoless double band decay, and solar neutrino searches, etc. So here is one example. For our neutrinoless double band decay and region, that is around 2.5 MeV, the preliminary optimization on the reconstruction is able to get 1.5% energy resolution. And the further improvement is still work in progress. And in the parallel, we are developing plans for the next generation, which is several tens ton liquid xenon experiment. The R&D of several key technology, including the low radioactivity, xenon isotope separation are being studied. As one example, we are collaborating with the Hamamatsu company and developing a new type of 2 inches square-shaped PMD. The radioactivity level of thorium and uranium is much lower than current 3-inch PMD used in the Panax photon. So we expect to have a better background control in this next generation detector. Another interesting study has been investigated. So we know the neutrino flow would be the goal of the next generation experiment. In the high mass dark matter region, the flow is mainly due to the atmosphere neutrinos. But due to the Earth's magnetic field, the distribution of atmosphere neutrinos is not uniform throughout the world. And from table, we see that the South China, where the CJPL is located, has a low neutrino flux, which is a unique advantage towards the neutrino flow. Okay, in the summary, the Panax 2 has completed in 2019, and Panax photon is the next. It has 10 times higher sensitivity as compared to Panax 2. So currently, Panax photon is performing offline tritium removal to reduce the background. And in parallel, we are developing plan for the next generation experiment at the CJPL. So please stay tuned and thank you.
Okay, thanks, Professor Zhou, for giving the very nice talk. So any questions from audience? Yes, Janine, go ahead, please.
Hello, hi. Thank you for the talk. I just had a quick naive question based on your very last slide. When you pointed out the advantage of this low neutrino flux, perhaps playing in your benefit to have a lower neutrino flow, I guess. I was just wondering in terms of order of magnitude, what are we talking about when you say low neutrino flux? How does that? Yeah.
So this is the neutrino flux as shown in this table. This is from this reference. They get to estimate the flux in different experiment laboratory. And the Juno is a neutrino laboratory, which is not far away from CJPL2. So the flux is only around 3,000.
Thanks.
Okay, any more questions? Actually, I have one theoretical question about your page 12. So you mentioned about the boosted dark matter. So usually when we calculate the dark matter scattering with either electron or nucleon, we use the non-realistic limit. I guess now we cannot calculate this in the in this limit anymore. And is there any difference between this boosted between the calculation in boosted dark matter or those non-realistic dark matter?
Yeah, so it's still in the framework of non-relativistic operator, even though it's boosted, but not that boosted. Otherwise, it won't penetrate. It would not penetrate through the Earth and get into our laboratory. So the cross section, the interaction cross section is still not that large. So you have it just to make sure the dark matter has a slight, just enough energy to produce KV level energy deposit in detector.
Oh, you mean the core energy is still small, although dark matter is boosted? So
Yes.
we can still calculate in the non-realistic limit.
Right, that's what the theorists point to us.
I see. Okay, thank you.
You can find the reference in this paper.
Okay, yes. Thank you. So any more questions?
I have a question. Unfortunately, I cannot raise my hand from my computer, sorry. So the question is very naive. Did you ever have noticed any annual modulations of your signals?
Yeah,
like,
for the
like Dama claims.
That's a good question. So the Pentax 2 has accumulated the 130 ton day exposure. So it's roughly around 1 year exposure. So the analysis is still working in progress. Yeah, we are checking this information.
So you could check whether you have some annual modulations in
right, but
in
only
a short while.
Yeah, so
okay.
Our exposure is just at 1 year, not that long. So we hope we can provide some information for this constraint. But we will see.
Thank you.
Okay, any more questions? So if there are no questions, let's thank Professor Ninzo again. Oh,
okay, thank you.
Yeah, thanks. And the next speaker is Zenip Dimiragli. So she will talk. She will talk about dark matter long-lived particle at Atlas and the CMS. So let's work on.
I just need a minute to set it up. I'm sorry, I apologize. I'm having a little bit of a trouble. Just give me a
no worry.
And hopefully this will work in a second now. I hope you can see my full screen now, correct?
Yes, yes.
Excellent, thank you. All right, so yes, today I'll be talking about dark matter and long-lived particles at CMS and Atlas, and I appreciate the previous speakers and questions about the dark matter production at the collider. So hopefully I'll try to maybe even answer and address some of the things that were mentioned in the talk as well. So certainly this is a large subject, and I just want to give a preview of that. I am not going to be covering all the dark matter and long-lived program of Atlas and CMS experiments in 20 minutes. I'm not delusional, but in this talk, I've chose to focus on a subset of searches. In the backup, you may find additional searches and additional results from both experiments as well. What I'd like to cover today is a selection of monadic searches and their strategies in general, to 2HDN plus pseudoscalar type of searches, so which corresponds to a slightly more complete model, so to speak. And then I'll also do a selection of fixed portal models, which I will link to further exotic couplings for the Higgs boson, which yield to long-lived signatures. and both from ATLAS and CMS experiments. So I want to set the tone by starting with what exactly we measure and how we interpret that. So in the beginning, I'll base my main talk on the WIMP-like signatures. Certainly, there has been quite a lot of effort on going in the hidden valley models and dark sector models as well. But at the end of the day, our observables are quite similar in the sense that we assume that this dark matter would be weakly interacting and therefore would leave no signature in the detector. And technically speaking, that's a disaster because if there's no signature, there's nothing we can detect. So what we assume is that this dark matter is produced somehow in association with some sort of a visible or a detectable particle in mono X type of searches. That's the initial state radiation most generally. And when you have a visible particle associated with an invisible particle, you can actually deduce the presence of this invisible particle by looking at the total transverse momentum of the system. And just by simply doing a momentum conservation, because in the initial state, you have initial transverse momentum is also 0, you can deduce this observable called missing transverse momentum, which is defined as the imbalance in the transverse momentum of the event. So the question then we ask is existing of this missing transverse momentum significant enough to be more than what we expect from standard model production? And if that answer is yes, is this dark matter? That's the question we're trying to target at the colliders. But this is not necessarily an easy task. Missing transverse energy is a very difficult variable, let's call it, because any spurious detector signal can actually fake this value. So as an example, on the left plot, what you're looking at is a simple dijet event, multi-jet QCD, which you expect absolutely 0 missing energy because it's balanced back-to-back 2 jets, right? But actually, when we first collect the data and then look at our data in the missing energy spectrum, what we see is what you actually see in these red plots. So those are the data that has no cleaning, just raw out of the detector, so to speak, as a function of missing energy. And then the shaded histograms are the ones that we expect from of standard model production. So our first step is to actually take this data and then understand that, that what are these anomalous sources of this missing energy. And generally speaking, these types of anomalous high missing energy sources tend to be due to things like beam halo particles, cosmic rays. These don't get reconstructed properly, therefore misreconstruction leads to missing energy. There could be particle striking sensors and the colorimeters and the photodetectors. There could be dead cells in our colorimeters. There could be noise in our readout system. So first thing we do is we take events that we know should not really have large missing energy and make sure that we identify all these anomalous sources, develop filters and algorithms to effectively reject these things, and then we start our analysis. And that's the starting point for any and all missing energy-based analysis in either of the experiments. And then comes the actual physics part. So we have, again, I will actually outline 3 main approaches to dark matter, but that's not all approaches I'd like to say. One approach is just going in a very simplified model route, where we moved from effective theories to simplified models in the sense that we can now probe what's happening in the interaction to some extent. We mediate this standard model to dark matter process through a mediator, and it allows us actually 4 parameters to scan, so to speak. The couplings, the mediator couplings to the quarks, the mediator coupling to the dark matter, and the mass of the mediator and the mass of the dark matter. Another area that we explored is through Higgs portal. Okay, there's Higgs, we all agree on that. And looking at the visible, expected decay of the Higgs, we can only constrain the Higgs branching fraction to a certain degree indirectly. So there's actually quite a lot of room, about almost 10-20% room still left to understand if the Higgs decays into something beyond what we expect from the standard model. So once you produce the Higgs, the question is, does that decay invisibly? And then another set is 2HDM plus A, so the 2 Higgs doublet models with a pseudoscalar. And it's actually quite a rich signature because it can end up with visible and invisible states. And it's a relatively complete benchmark, especially compared to a simplified model, which has a lot more parameters that one needs to worry about. So I'll give a brief summary of a few analyses that cover these types of models. So in the case of the simplified models, as I briefly mentioned, we moved away from the EFTs into these simplified models, and that gave us ability to probe a little bit more about the possible dynamics of how this process could be mediated. We study specifically spin 1, spin 0 mediators. I'll cover a few spin 1 examples, but when it comes to spin 0, I'll try to focus a little bit more on Higgs directly. But there are different mediator processes that we also study, like vector axial vector and scalar and pseudoscalar models. Probably the most one of the most important searches when it comes to these simplified models are these mono X searches, and within the mono X land, monojet and V signatures are the ones that stand out first. I'd like to note that very similar strategies are pursued both in ATLAS and CMS, and the whole premise is that you look for a very large missing ET and existence of one or more large energetic high energy jet. Generally speaking, we are moving in the direction of using more boosted machine learning based taggers, especially for things like a boosted V, like a W or a Z boson. And then we generally clean our events by rejecting any presence of any visible energy beyond the object of jet or the V. The beauty of these particular analyses, both ATLAS and CMS, is that in the first talk, there was a mention about that these searches are hopeless because the irreducible background uncertainties are larger than the signal. It used to be true in the past. However, the beauty of these analyses is that now, with the use of data control regions, we actually build ratios between, for instance, to estimate a Z nu background, we build ratios between the Z nu, which is the invisible process, and Z mu or ZLL in general, which is a visible process that we can very well detect and we can very well constrain. And by building ratios to constrain the Z nu background in these types of invisible searches, we are able to reduce our uncertainties in a very drastic way. So to give an example, at the moment at around the TeV range, both in ATLAS and CMS, we're only talking about a 5% uncertainty. And since we're only trying to probe how the spectra is changing, this uncertainty is indeed very important. And this constraint allow this new method of estimating really allows us to probe dark matter signals very effectively. I'd like to also note that both of these experiments are working extensively on providing materials for allowing for everyone to do reinterpretations. There is now MAD analysis implementations of the full frameworks. There's recast software framework available as well. Even ATLAS released another results that use the ATLAS monojet results using the recast software to do a dark Higgs interpretation as well. But the actual results, the first bread and butter results of these types of searches actually is targeting to probe the dark matter mass as a function of the mediator mass. And obviously the goal is to probe always higher and higher masses. We are actually almost reaching a TeV dark matter range as well. And with more data, this bound is only obviously going to improve. But one thing I'd like to note is that the coupling choices. So we have agreed on a set of coupling choices between the experiments that we scan. However, obviously this doesn't have to be what nature is. So it's quite important that we also keep probing, for instance, in different variables such as the coupling. So we have studies where we have fixed one coupling and the ratio of mediator to dark matter mass and then probe. So our goal is to always push for higher mediator masses and always push for lower couplings, which will end up, which are the regions that we are trying to move forward to. And of course, we can compare to the rest of the world just to see where we stand. Essentially, again, these plots should be taken with some grain of salt because of these coupling choices, and these coupling choices can change not the shape, but overall scaling of our bounds. So here you see a comparison with respect to the spin-dependent proton cross-section and the neutron cross-section, essentially. The red ones are the ones coming from the colliders, whereas the blue ones are coming from the other direct detection experiments. And then on the last one, you have the spin-independent nucleon cross-section sensitivity comparison as well. Generally speaking, one way or another, we in the colliders, I think that the theme is that we are able to probe lower masses effectively. And as you can see, it's roughly a flat exclusion across a certain dark matter mass. And that's mostly because our sensitivity is driven by our, as mentioned before, our background estimations and our uncertainty on those background estimations. So our limit is our limiting sensitivity limiting factors are those things. I'd like to take a somewhat of a side note and then discuss something quite interesting. So I've mentioned while I was focusing on the WIMPs, you know, which gives you a complete missing energy. And there are quite a lot of signal models that actually introduce a dark sector with multiple flavors of dark quarks that are charged under a dark confining force, which results in some stable and unstable dark hadrons. And then the stable hadrons would then be the dark matter candidates, and while these unstable hadrons would decay promptly into these standard model quarks. And that's actually quite an interesting signature, because what you end up with is a jet that is somewhat semi-visible. So just to put it in a context, when I say semi-visible, we're looking at the ratio, for instance, of stable dark hadrons to all dark hadrons. And if, you know, all of them are stable, then you're looking at something like a dijet signature, and all of them are unstable, you're looking something like a monojet signature. But we've never probed somewhere in between, in the sense that what if it's semi-visible? So there has been a very dedicated search in CMS that looks for these types of signatures, where you actually have, instead of the missing energy being anti-aligned with your jet, you have missing energy actually aligned or very close to your jet, which is a relatively notoriously difficult region to search, because that's usually what multi-jet background also looks like as well. So this analysis have utilized quite a lot of machine learning techniques to deduce dedicated taggers for these semi-visible jets, which resulted in being able to lower the backgrounds by orders of 100. And the strategy here was to look at the data and then do almost like a widened hunt in the MT spectra, which is the transverse mass spectra. And by fitting the background directly in the data and looking for these deviations, they're able to get quite sizable bonds on how invisible the jet can be versus the mass of this mediator. Just to take back, just to bring back the WIMP subject together, even though I just discussed monojet and somewhat of a semi-invisible jet, it actually, if you put it all together, there's quite a lot of different searches being done. I'd like to call it monomania, because we do all mono searches, so to speak. We do a monophoton. Okay, photon is the radiated object. We do a mono-Z, where Z decays leptonically. We have the hadronic decays. We have the monojet, mono-V. We have dijet searches. We have trijet searches. So our goal is to cover this entire mass spectra as much as possible. You may wonder, why do it all? You know, if you look at it, for instance, in the mono X direct dark matter searches, so to speak, monojet can do, you know, say so much better than a mono Z. You know, why even bother doing mono Z? Well, the idea is that we don't know what this dark matter looks like, right? So it could be completely different, and the simplified model is certainly not what the certainly is not the entire truth. So if you were to, for instance, look at more complex models like 2HDM plus a pseudoscalar, which has like a pretty much the only ultraviolet complete and renormalizable theory we have at the moment in this context, you see that different searches like mono-Z excel. So in this particular models, you assume that the standard model Higgs is part of this extended Higgs sector, and it has two complex Higgs doublets and a pseudoscalar. So you see the diagram here. So the pseudoscalar mediators are not necessarily too strongly constrained by the direct detection experiment, and this is yet another reason why we are very interested in searching for these things. Technically speaking, it has quite a number of independent parameters, which makes it quite difficult to pinpoint. But after looking at other experiments constraining the parameter phase space, agreeing on some fixed parameters, at the end of the day, both Atlas and CMS have agreed to scan, with the guidance of theorists, agreed to scan 5 free parameters as listed here. So which is the heavy Higgs mass, pseudoscalar mass, a dark matter mass, mixing angle between the two CP-odd states, and the tangent beta. A few interesting things is that while I'm showing you here the gluon fusion mechanism, there's also the BBA mechanism, which gives you different sensitivity at different phase spaces of these scanned parameters, which I'll discuss in the following slides. And again, this is quite rich in signatures because you can get a Higgs boson signature, you can get a Z boson signature, and we'll look at these now. One of the things, as I mentioned, so this mono X search line in the WIM plant, mono Z was quite unimportant compared to, say, a mono jet, but here it really shines as mono Z type of searches is the most sensitive, one of the most sensitive searches for these types of models. What you do is strategy is simple. You look for 2 leptons compatible with the Z. You require large missing energy. You veto an additional activity. You model all your backgrounds through this data-driven ratio method that I've described. And then to maximize sensitivity, you actually look at observables that relate directly to this type of model, such as transverse mass and missing ET. I'm here showing the links to the result, the distributions to the Atlas and CMS results. Unfortunately, no excess has been seen in either of these searches. In a few minutes, I'll actually show the final results of these types of approaches as well. Another interesting model, again, that relates to the 2HDM type of things is the mono HBB. And here you have the BBA production, and then you have the gluon fusion production. Here the Higgs decays into BB bar. And there you can have, in this Atlas just released a new paper on this using the full data set. CMS's early results only contain the early 2016 results. But the idea is that you go in the direction of categorization in these types of searches, because this Higgs decay, depending on how boosted the Higgs is, could be a split resolved BB bar process. Depending on how boosted Higgs is, it could be a merge signal process. So to cover it, these types of analysis are devised to have a multiple signal region. In these plots, I just highlight a few different places where this analysis particularly was binned in B-jet multiplicity and also missing energy. So here you see a 2 B-jet multiplicity at relatively low missing energy, which corresponds to a particular final, a particular topology, and on the right hand side, a resolved topology, and on the right hand side you have a merged topology where you have multiple B-jets, more than 3 or more, with very high missing energy. And again, the same strategy is applied here. The backgrounds are estimated using data control regions, and by doing ratios, you're able to constrain most of the uncertainties very effectively. Another type of search is the single top type of searches. So we're looking at a T-channel process of TJ, essentially top and a quark and 2 dark matter particles. And it's these types of processes actually, the first 2 diagrams that you see interfere actually destructively. That way, it ensures unitarity in these types of processes, and this destructiveness actually changes as a function of the charged Higgs mass. On the other hand, you have the TW production, and again, these are quite dominant production modes for dark matter plus top cross section, and these also can interfere destructively. And when you have this kinematically possible, this particular decay Higgs to W and A, it actually produces sizable event rates that it can be searched effectively. Atlas just released a result on this, mainly focusing on 3 independent categories again. And these categories, these are different bins of those categories. These are the signal categories, and they are grouped based on lepton and jet multiplicities to maximize the sensitivity. On the right-hand side, I think this plot is particularly pretty. You can actually see what type of uncertainties remain in any of these regions. You can see that whenever you see something like a background normalization, that's even though there are control regions employed, certain backgrounds are notoriously difficult. And you can see in what cases these backgrounds are, this contributes to total uncertainty. You also see effects of detector, which corresponds to our simple, calibration uncertainties like jets, missing energy, and things like that. And then you have the theory modeling, and as you can see, how much the theory uncertainty interplays with experimental uncertainties. Putting it all together, so actually there has been a combination paper both in CMS and Atlas, CMS with earlier data set and Atlas with the full run 2 data set that puts all of these 2 HDM models into the same footing. On the first, there's multiple scans that are being done. For the lack of time, I'm just going to highlight the 2 of them. Here you're looking at the heavy Higgs and the pseudoscalar mass scan, and on the right hand side there's also the variation with respect to the tangent beta. As you can see, for the majority of the cases, the mono Z, so ZLA plus MET, and mono H, HBB plus MET type of processes dominate. Depending on what processes come in and out, what production modes are effective, you might get less sensitivity in certain cases, for instance, here in the HBB bar case. And then here, for instance, you can see that due to different experimental techniques, like, for instance, using Z to trigger on as opposed to missing energy, certain processes can lose, certain analyses can lose sensitivity in very low masses. So this is also why we have to target all of these searches at the same time to be able to cover the full parameter space. Another process that I'd like to kind of briefly discuss is these dark Higgs models. So it's obviously not a 2HDM model, but it is almost like a Z prime model essentially. So again, it has quite a lot of parameters that one can probe, the masses, the couplings. And in these types of models, Z prime mediator is responsible for establishing some sort of thermal equilibrium between the visible and the dark sector in the early universe. And these dark matter particles acquire their mass through the interaction with the dark Higgs boson. So you can see actually what kind of processes, what kind of final states are quite important. So below a certain, kinematically turning on and off, depending obviously on the existing masses. And you can see that Higgs to W, the S to WW is quite dominant after a certain mass range. So this is particularly targeted for everything. I think I'm running out of time, so I'm going to speed up. I apologize that I spent a little bit more time than I intended. These types of searches, again, quite heavily rely on three-dimensional machine learning algorithm, three-dimensional likelihood fits, scanning multiple variables to extract the maximum amount of sensitivity. Another set of models that I'd like to briefly talk about is the Higgs portal. Again, I'm speeding up. Please ask me questions. I'm sorry that I mismanaged my time. So the key point is, how do you produce the Higgs boson? The final state is met, yes, but initial state, how you produce Higgs is actually what determines your signature in these kinds of searches. And obviously the most notable thing that you will immediately jump to is VPF type of topologies, VPF production, because it's so unique in signature with 2 forward jets in the detector. It's a very prominent signature, but also the background looks as usual identical, which is why one uses the exact same strategy as mono X searches to constrain these backgrounds to employ the control regions. And at the moment, with the direct searches just singly in Higgs invisible land, observed limits at the moment go down to 13%, which says that, like, Higgs boson could not be decaying into with 95% confidence level into invisible final states more than 13% of the time. Higgs and CMS results, CMS and Atlas results could be accessed from these links. You can also do more interesting things. You can say, okay, what about I have this VBF final state, it's very unique, but let me add a photon tag there. Let me have a photon be radiated from a W there. Then you even constrain further your phase space and reduce your background dramatically. And that's what's done here. So you tag another photon. And similar jet selection to the VBF searches, additional low PT searches, and then you employ neural networks to optimize for the signal, and the branching fractions from this channel alone ended up being on the order of like 35%, roughly speaking. But you can also put all of this together and combine with all other channels. So CMS does not have a full run-to result yet. This is a 36 inverse femto-1 result, and Atlas has about full 13 TV data set as well. The current best limit on the invisible branching fraction of Higgs right now is about 10%. That's 11%. I'm sorry, that's quite remarkable. And you should see updated results coming from CMS soon. And by combination, what I mean is obviously the different production modes. So I briefly discussed the VBF. ZLL is the one that we discussed, mono Z. Mono V is what we would call the VQQ, like the VH production, and then mono jet would be the gluon fusion production. And you can see this step-like structure in the sensitivity. All right, so I'll just 2 minutes, I promise. I want to briefly touch upon long-lived signature. Long-lived is extremely rich in phenomenology. It can answer a lot of questions. Today, I just wanted to focus on the exotic Higgs decays that relate to dark matter specifically. And in addition to being extremely rich in terms of understanding, the nature, it's also extremely rich in its signature because, you're pretty much opening up your entire detector for the particle to decay in. We've already covered that there's sufficient freedom to explore exotic couplings of the Higgs. And if the decay product is actually light or coupled with small couplings, then you end up with long-lived particles. The problem is that the CMS and Atlas detectors are designed for prompt decay, so it's notoriously difficult, the long-lived searches, because the triggers are not designed that way, reconstruction algorithms are not designed that way. So even just noise, simple electronics noise in the detector could look like a signature. So it takes quite a lot of effort to carry out these searches. So there could be strategies of looking for things that are quite generic. So in this case, for instance, we're looking at a Higgs decay into two long-lived scalars that decay into two positively charged same flavor leptons. So these leptons are going to be displaced, but in this particular search, you require a common vertex. And the key variable here essentially is the impact parameter of these leptons with respect to the beam spot. This search was carried out in 3 different final states, and certain sensitivity limits were set as a function of the C tau and the branching fraction of Higgs to long-lived scalars. You can do more dedicated searches, of course, as well, which will be a lot more sensitive than generic searches. And again, because the triggers are not necessarily particularly designed to look for these displaced objects, you can actually you can create an associated production, say a ZH, and then you can trigger on the Z, and then you have complete freedom on the Higgs line. And if it decays like, if it has a long-lived particle decay, then you can still change your reconstruction algorithm after collecting the data to search for these things. And that's exactly what's done here. So tag the event with a Z, and then develop new reconstruction algorithms to create displaced jet tagging, rely on the impact parameters, transverse angle, primary vertex associations, and then look for sensitivity. Again, the most important observables in these kinds of searches is going to be how many displaced jets you can see. And based on that, both Atlas and CMS have released sensitivity that's quite comparable in terms of these types of 2L, 4B final states. The very last analysis that I want to briefly mention is we're going quite, I think, becoming quite imaginative. For instance, another approach to this this Higgs to 2 scalar type of searches is with 4 jets is looking at these jets using the muon detectors. The muon detectors are the outmost detectors of Atlas and CMS. So technically speaking, you're not talking about tracks, you're not talking about jets. Instead, you're actually talking about clusters in the muon system. So almost like re-envisioning the muon system like a sampling calorimeter. Atlas also developed additional standalone vertexing based on the Atlas spectrometers, Atlas muon spectrometers. And these types of ideas are now currently being developed and studied quite extensively. Both Atlas and CMS published recent results using part of their muon systems in these types of things. And I think in the next generation of CMS and Atlas searches, you'll see more and more dedicated triggers to collect data rather than relying on, say, traditional MET-based triggers for these types of searches. On that note, I just want to conclude. At the moment, the standard model seems to continue to stand strong. However, I want to note that it's only about 10% of the data delivered and collected. So there's kind of plenty of time and room for more novel ideas, more techniques, and more discoveries. Thank you.
Yeah, thanks, Geneva, for the very nice talk. So maybe we can have one quick question. Yeah, Manu, please.
I just wanted to clarify that I never claimed that these mono-X searches are useless. For on-shell mediators, certainly you are sensitive. However, to achieve sensitivity for off-shell mediators, your error has to be below 1%. 5% is not good enough, I'm afraid.
Yep, I would agree about the off-shell. Off-shell is just, yep. Thank you for clarifying.
Okay, thanks. I think we should move faster to the next.
Apologies for the time issue there.
Okay, no problem. Okay, our next speaker is Professor Bhaskar Datta. So, Bhaskar, can you start to share your screen?
Yes.
Yeah.
Can you see?
Yes, yes. So he will talk about sub-GB document. So let's welcome Professor Datta. Okay.
So let me first thank the organizers for this excellent work conference and inviting me to speak here. And I know from a first-hand experience what sort of effort that goes into organizing such a huge workshop successfully. Kudos to the organizers. Okay. So, of course, dark matter exploration requires new physics, and the scale of new physics can be wide-ranging, and dark matter can be thermal, non-thermal. And in the thermal description, the dark matter was in thermal equilibrium in the early universe with the background radiation, and the abundance gets calculated by solving the Lee-Weinberg equation. Now, in the non-thermal picture, dark matter gets produced from the decay of some heavy particles, and it was not in the thermal equilibrium when it was created. And the mass range of this non-thermal dark matter is, of course, larger than the thermal dark matter. Now, the dark matter sector is associated with new scales corresponding to the dark matter particles and the mediators. And if this mass scale is greater than GeV, it can be searched at the LHC. However, if the mass is less than GeV or sub-GeV range, things become dicey. And however, there exist many interesting models in the sub-GeV range, and they explain various anomalies in different observations, for example, RK, G-2, mini-boon, etc. And also they explain the neutrino masses and mixings. So in this talk, what I'll do, I'll be concerned with these models where the mass scale for this dark matter and mediator is sub-GeV. So what I'll do, I'll discuss a typical sub-GeV dark matter model, and then which can be generalized to many such models. And then I'll discuss the constraints, typical constraints in the model parameter space of such light mediator and light dark matter model. And then, of course, I'll then discuss the possibility of detecting this model in the direct and indirect detection experiments. And then I'll discuss how to probe this sub-GeV dark matter model at the ongoing beam dump experiment is specifically for neutrinos, and which are already showing to be quite effective in investigating this low mass dark matter model, and which has quite small couplings. And then I'll give my outlook. So let me start with the model, and this is a typical model. And so the motivation for this model is the tremendous hierarchy of quark lepton masses in the standard model. And in order to address this hierarchy, one can think of introducing a new mass scale around a GeV associated with the first generation, and this new mass scale is associated with this spontaneous symmetry breaking of this U1 P3R, and the associated charges are this, our charge assignments are for the right-handed quarks and leptons and neutrinos, and then the eta L and eta R, they also have charges under this T3R, and they form this dark matter, like a eta 1 and eta 2 eventually, and then phi, which breaks this symmetry as a -2 charge, and this is an anomaly-free assignment, and what we get out of this would be a light dark matter, which is from this combination eta 1 and eta 2 with a small mass gap between them, and also a light gauge boson mediator as well as a light scalar mediator. So that means there are 3 light particles in the sub-GeV region. And the predictions are, of course, testable at various low energy experiments, and this model accommodates this G-2 anomaly and RK anomaly, etc. So, and of course, these models are created to have light dark matter. So one can explain that thermal relic abundance, if one goes for that in this model, like it has 2 mediators, scalar and vector, and so it can have both S wave and P wave possibilities, and depending on masses and couplings, one can have one over the other. In the S wave possibility means the annihilation sustains even today, and P wave it goes away because of this velocity separation. And so here are some few cases, benchmark scenarios which arise in this model, again by choosing the couplings and masses accordingly. So now similar models, like it has, has been constructed and can be constructed in this same line, like by having new gauge symmetries like U1B, U1 L mu minus L tau, etc., etc. And there are lots of works in this direction. And also one can extend the Higgs vector to have a light scalar or pseudoscalar mediator and plus sterile neutrinos. In such a case, one can also accommodate warm dark matter, and depending on the parameter space and all this stuff. And so, of course, people also have looked into various string construction to motivate a low mass dark photon. And here is an example. This reference has looked into various such possibilities. Now, one thing though, this though it's a sub-GeV, so one may think that we don't have many experimental constraints, but actually it's not true. There are many experimental constraints that are like emerging from various low energy accelerators G-2, and then astrophysical cosmological constraint, etc. And so one needs to be mindful about these constraints when one builds a model, sub-GeV model. And however, there exists lots of free parameter space as well when one digs into this, into the detail. And the model would survive in those parameter space and would make prediction. And also, this is one typical scenarios or the constraint scenario. And depending on the models, this may change. And so for example, the T3R example I showed, it has 2 mediators. So all these constraints need to be recast in the context of that model. So now the question is, how do you probe such model? Now, the direct detection experiment, typical sub-GeV dark matter has a problem because it does not have enough energy to produce observable nuclear recoils. So new ideas are needed, and there are many ideas emerging, in this direction, like which uses various low threshold possibilities. Then you use electron target Migdal effect, atomic coherency, photoelectric absorption, then using new materials to probe this sector. And actually, this has become a kind of a hotbed of new ideas and new approaches to probe this kind of scenarios. So let me start with a few of them. And actually, in the morning, or it's a morning here, night there. So we already heard a talk from the Panda X speaker regarding this Migdal effect. Like here, the dark matter just kicks the nucleus, and the nuclear recoil is not large enough to be observable, but the nucleus shakes off an atomic electron, and the signal is observed in the form of electromagnetic energy deposition. And if the with a low threshold detector, one can identify such a signal. And in fact, this Migdal searches can be very effective in probing low mass dark matter. As you can see here, this is the gray region is the nuclear recoil constraint, and then this blue, green, orange shaded regions, they are using this Migdal effect, and you can see that dark matter mass can go down to 10 MeV in terms of these searches. And in fact, there is a new Sensei sensitivity search, and where one can find that using this Migdal, dark matter search limit can go down to even 600 keV. So now one can also kind of utilize this Migdal effect to look for this inelastic dark matter scenarios. The interesting thing is that if one uses the exothermic scenario, one can probe not only a very small dark matter mass, even using the existing data from Xenon 1 ton, but also one can probe smaller couplings. There you can see that the G chi times Gn, it has gone down to 10 to the minus 11. So, but the elastic scenario sensitivity is not that great, but also the endothermic and elastic, they are not that much as this exothermic one. So now also another possibility is cosmic ray scattered. Also, we have heard that from the Panda X speaker, and in this case, the low mass dark matter can become energetic, and by hitting these cosmic ray particles like helium, hydrogen, electron, etc. And then this boosted dark matter now ameliorate this need for this low threshold detector to a certain extent, and here is a plot of nuclear recoil, and you can see that this is the light mediator scenario, and the dark matter search can go down to below MeV, and also for a smaller cross section or a smaller coupling. And so now also one can utilize the electron recoil in such a case, and since the need for low threshold is a little bit ameliorated. So that means that one can utilize a large neutrino detector in such a case to probe this kind of scenario. And you can see that super K, feature hyper K, or Dune can do much better in probing this kind of parameter space. And so this is a scalar mediator there for M5 of very light EV range, 10 MeV range. And you can see the cross section, how much of a cross section these detectors can probe in future. So now also another interesting thing is to use this dark matter electron interaction. And also we have seen that Panda X would do quite good in the future, but currently DAMIC and Sensei, they give you the leading constraint, and the dark matter mass can, the reach for dark matter mass can go down to less than a MeV. And here is xenon 10. This is for a heavy mediator. For light mediator, you get the similar mass reach, but here the cross section can be reach can be lower. But it costs less energy to produce a recoil here, but the calculation becomes very complicated, because now you are dealing with the electrons in the atomic potential, and so the form factors are much complicated here. So, but accurate, lots of accurate calculations are emerging, including various transitions from valence to conduction, conduction to free, valence to free states, and all these works are very important for this upcoming or the ongoing observations and Sensei, DAMIC, Edelweiss, and all these experiments. And also, this electron recoil scenario seem to be could be the reach could be better even compared to this Migdal effect, at least for light mediator. One can see this from this reference, and these authors consider this silicon detector. And now these are sub-GeV. For sub-MeV, the proposal is to use superconductors, superfluid helium, Dirac materials, polar materials, and various stuff. So there are lots of activities and new ideas coming up in this area. So how about indirect detection? Now the indirect detection is also like a Fermi-Lat, CTA, E-grade, they can come down to 1 GeV, but below a GeV, again, it becomes a problem. But however, the upcoming Amigo e-astrogram should be able to probe this dark matter down to a MeV, and with a kind of very high sensitivity, you can see that. Also, a square kilometer array could probe small dark matter mass with a down to a small annihilation cross section, and this one can utilize the inverse Compton scattering emerging from these final state electron positrons from the dark matter annihilation, and this inverse Compton scattering happens against the CMB background. In various galaxies and galaxy clusters. So here, Coma is given this line, and Omega Centauri is for different diffusion choices. So the diffusion parameter is a little bit of an uncertain there, and but for two extreme values, one can see that how much the parameter space that can be constrained. Okay, so now let me turn my attention to another possibility, because as I said, like there are various new strategies are coming up to probe this sub-GeV sector. So this is another one in this game. So here, instead of using this ambient dark matter, this strategy uses the lab-produced dark matter and to probe this dark matter parameter space. And so in this strategy, one utilizes this beam dump facilities geared for neutrino experiments. And here, for example, the protons with energies 1 to 100 GeV, depending on what kind of experiment you are looking at, they hit a target like with the beryllium, mercury, tungsten, etc. And when the proton hits a target, it produces not only the neutrinos, these are neutrino experiments, so you expect them to produce neutrinos, but it also produces photons, electrons, and all this stuff. And so similarly, one can do these kinds of stuffs at the reactor-based experiments, where also you produce not only the neutrinos, also a lot of photons. So what amount of photons? So here is a simple estimate, if a 10 to the power 5 protons hits a target, we have 3 examples. Like here, coherent uses a 1 GeV proton beam, CCM 800 MeV, JSON square is about 3 GeV. So, and you can see that 10 to the power 5 protons produces that amount of photons. So lots of photons, for coherent experiment, which is all 3 are running, coherent has already given us results, and there you find about 10 to the 23 protons is the target. So that means that amount of photon you expect to be produced in this experiment. Now, what do you do with these photons? So photons kinetically mix and then produces dark photon, and dark photon decays to dark matter. And so all of a sudden, that means you produce you are able to produce lots of dark matter in the lab. And not only that, in this case, dark matter, they're not virial velocity limited, so it can have higher energy, and most of the cases it does, because they are produced from these light dark matter produced from the, for example, from the meson decays, and then the low threshold detector need is not that much to detect this very low mass dark matter, and then the dark matter comes to the detector and then hits the nucleus, produce a recoil, and then you observe it in the same way as you do in the dark matter detection experiments. But however, the problem is just like the ambient dark matter, where you see a neutrino flow, nature created neutrino flow, but these are neutrino experiments. So what do you expect? You expect lots of neutrinos also coming to the detector, and so they would create a background. So a different kind of neutrino flow, but this time it's produced in the lab. And these are the typical things. So one thing that this quartz produce dark photon produce this dark matter. So this is the mediator. So same mediator also appears in your direct detection experiments, because there also dark matter interacts with the quartz by similar mediators. And this is a typical expression for these detection cross section, and as a function of this recoil. And let me first utilize one specific experiment so that you understand what's happened to the neutrino background, how do you handle it, and how do you really probe the dark matter parameter space. And in this experiment, you have a 1 GeV proton beam, which hits the Mercury target, and then when it hits the target, and then it produces all these pions, muons, and also the new mu's, new electron type neutrinos, muon type neutrinos, and the pion is a prompt decay, and then muon is delayed about a microsecond, and so this is the prompt, and this is the delayed structure. So the experiment gives us the both timing and the energy distribution, and the data is available publicly, so one can do a dark matter analysis by using this data. And so the coherent in 2017 found that this coherent elastic nucleus scattering events to be at 6.7 sigma, and this is a coherent scattering, because the energy that's transpired to the nucleus is small, and so that means the whole nucleus as a whole recoils, and so which gives you a squared enhancement in the rate. And now it has become 11.6 sigma based on the second round of cesium iodide result. And with a liquid argon, they found 3.8 sigma excess in the coherent elastic neutrino scattering events. Now, similar experiments are also ongoing at CCM, coherent Captain Mills at Los Alamos, 800 MeV, and JSNS squared, and also the reactor-based experiment which proves this coherent scattering are like a CONAS, CONI, and etc. and also minor Texas A&M. And so now the question is, what's the neutrinos? How do you handle the neutrinos? Those are coming from this stopped pion decay in these experiments. But since this experiment gives us both the timing and energy spectra, one can utilize them to reduce the neutrino background in this case. So for example, we have found that the prompt neutrinos emerge from the pion decay and delayed from the muon decay, and dark matter is promptly produced. And so that means one can look for a timing region which is less than 1.5 microsecond to beat the delayed one, and to be in that prompt window. But the prompt window, you can see that you have lots of prompt muon type neutrino background. But since these muon type neutrinos are produced from the pion muon mass difference, so it has a definite energy cutoff. So you can use an energy cut to remove these neutrinos and to go for this dark matter signal. And the dark matter, of course, the recoil associated with the dark matter production, the energy is not limited as the between pion as a pion muon mass gap. So you can utilize this. So that means there is a neutrino floor, lab created neutrino floor, but using this timing and energy spectra, one can remove that neutrino irreducible neutrino background, at least in this lab experiment, to look for dark matter. So now once after you remove the background, now we can look for this dark matter model, any dark matter, light dark matter model. And this is the current constraint. This red line comes from this combining this cesium iodide and liquid argon data. And this orange is the future JSNA square, and then CCM. But JSNA square and the CCM lines, what you have put here, they are we assume zero background because we don't know the background from those experiments yet. But coherent, the data is with the background, so the background is included. So this is a realistic line. So one can see that one can really probe sub-GeV mediator. And also the dark matter is 1/3 of the mediator, so a very low sub-GeV or very low dark matter mass. And this line goes kind of continuous, so you can you can probe as low of a dark matter mass as you want to. And so another interesting thing is this GN-G chi, or this coupling, dark matter coupling to the mediator and the mediator coupling to the nucleus, and which is less than 10⁻⁵ for this mass range. And this actually is better than the direct detection experimental limit at this stage. And so also it would improve in the future. So the previous one, the example I just showed is based on this proton beam colliding with the target. But now also there is an experiment which is ongoing, is the LDMX, light dark matter search, and it uses the electron beam, and the measurement is based on the missing momenta. So in this case, dark matter does not appear in the detector, but it's a kind of one measures the missing momenta. And the constraint also is quite good. It's the dark matter electron coupling. You can see that it can go down to 10⁻⁻15 in the Y value, and correspondingly GE, G chi also is very small for this mass range. And so upcoming, so one can use this, various upcoming neutrino facilities, for example, DUNE, and with a near detector facility, and then various neutrino program like SBND, Icarus. Icarus is ongoing. So one can, again, probe the dark matter parameter space. In fact, here, these analyses are done using that target mode, that means beam hits the target, but also one can use the beam dump mode, beam hitting the dump, and then actually one would increase this reach of this parameter space. And for lepto 4-bit model, the reach is quite extensive. As one can see, that's coupling goes to 10 to the minus 7, minus 8. For obvious reason, these are all proton-based experiments. So that brings me to the end of my talk. So the outlook, so what's the scale of new physics? That's the question. And models with sub-GeV dark matter seems to be very interesting, and especially with the light mediators, and they can explain many of the anomalies like G-2, RK, mini-boon, etc., etc. And models have allowed parameter space even after satisfying various experimental constraints. And these models can be probed in direct, indirect detection experiments, as I showed. And the ongoing neutrino experiments are they seem to be also providing leading constraints in the parameter space. And in the upcoming days, one would use various neutrino on experiments and other beam dump experiments like LDMX to probe interesting constraint in this parameter space. Thank you.
Okay, thanks, Pascal, for the very interesting talk. So any questions from audience? Question or comments? So I don't see any. Maybe Pascal's talk is very clear, I think. So if there's no more question, maybe we should move to the next talk.
Thank you.
Thank you. So our next speaker is Pedro Suarez.
Hello.
Hi. Yeah.
Can you hear me? Yes.
Yes. You can just start to share your screen.
Yep.
Okay. Yeah.
Can you see it?
Yes.
And my pointer as well?
Yes.
Okay, perfect.
Yeah, please just go ahead.
Yeah, thanks a lot for inviting me to speak at this conference and for organizing it in this difficult times. So I will be talking about gravitational waves as probes of new fundamental physics. So I will be changing gears a little bit from laboratory experiments again to observing the early universe using astrophysical data. So here's a brief outline for my talk. So I will talk about gravitational waves and why they are a good window into the early universe, and then present some work mostly from my group with these people here about gravitational waves from first order phase transitions, how they could help us probe dark sectors, and then also on gravitational waves from new physics models that contain axions or relaxions. Okay, so let me get started by looking at this wonderful picture from NASA. I think I should eventually put a copyright here. So this is all we know about the universe from direct observations. So we start by observing the stars and galaxies, and then as we go further back, very early stars. And the earliest thing we see directly is the CMB. So the radiation that was emitted 300,000 years after the Big Bang. And this is, of course, all very nice. But the problem is that most of the things that I'm interested in as a particle physicist happen before that time. For example, the breaking of the electroweak symmetry in the early universe, nucleosynthesis, all sorts of phase transitions, for example, the QCD transition, and also maybe the things that we haven't seen yet, for example, the origin of dark matter when it is produced, or the production of the visible matter in the universe. All this probably happens before the CMB is emitted, and we will not be able to observe this period of the early universe using photons. Yeah, this is simply because the universe is not transparent for photons at earlier times. And the nice thing is that now, since 5 years, we have a new tool that can carry information from the very early universe before the time of the CMB to us today, and these are the gravitational waves, because they can propagate essentially from any time shortly after the Big Bang. You know, once your relevant scale goes below the Planck scale, and gravity becomes a weak force. So any phenomenon in the very early universe that produces gravitational waves could potentially be observed today by measuring those gravitational waves. And this is something that now we are able to do, and we will hopefully continue to do in the coming decades. So what are possible sources of primordial gravitational waves? So not what we see today, gravitational waves which are emitted from nearby or somewhat far away stars. These are astrophysical sources. No, I'm interested in sources of gravitational waves in the very early universe, so primordial sources. And the key examples that have been studied a lot in the literature is first order phase transitions. So from symmetry breaking processes, for example, from electroweak symmetry breaking, inflation and reheating. So inflation is known to produce gravitational waves. We don't know yet how many, or with what intensity, because we haven't seen them yet. Cosmic string networks can produce gravitational waves. And as I will argue later, also certain models of axions lead to an observable gravitational wave signal in the early universe. Okay, so I looked a little bit at the parallel session talks, and I saw that there were many talks on a variety of these topics. So if anything, you feel I'm treating too superficial here, go look at the parallel sessions, and you will certainly find more details and also more up-to-date results, for example, on predictions of the gravitational wave spectra from first order phase transitions and so on. Okay, so here I will focus mainly on the first and on the last case, so phase transitions and axions. But let me make some more general comments first. And this is regarding what we can learn from these gravitational wave observations. And for that, I show you here two pictures, or two figures. The first one, the green curve, is the characteristic signal of a first order phase transition with a temperature of order 100 GeV. So you see here that it has a clear peak, and then it has it falls off at high frequencies and low frequencies. And this is something, at least in principle, is calculable for a model. Yeah, and you can compare it to your observation. And what's been particularly interesting, in particular, if you think about the first time that we measure such a signal, is that the peak, so the easiest bit, that's the thing that might be detectable first, is correlated with the temperature at which the phase transition happens. Yeah. So immediately, if you see such a signal, depending on which experiment, for example, here's the sensitivities of LISA, this is some older figures, LIGO, pulsar timing arrays. Immediately you learn something about what scale of new physics the signal would correspond to. And then also the shape is important. For example, down here there's a somewhat old prediction for a cosmic string model, where you see it, instead of having a peaked structure at the observable frequency range, you have a very flat spectrum, and then this peak happens much later at frequencies that we cannot observe today. Okay, so the basic statement here is that by observing or by looking for these gravitational waves, so this gravitational wave background from the early universe, we might not only see some trace of new physics, but we would be able to by measuring it more and more precisely, we will be able to learn something. We might be able to distinguish models and so on. And I have some examples later to see that this might already be, this can already be done with the very first bits of data that you collect. Okay. The other thing that's very encouraging in this field is that there is there are a lot of experiments going on And in addition, new experiments that are being planned, built, approved, constructed, and so on. So the one experiment that you all know, LIGO, is not on this plot here. This is ongoing. So what you see here is the frequency of gravitational waves from very small frequencies, inverse years, to very high frequencies, what are hundreds or thousands of hertz. And over here on the y-axis, you have the intensity. So the fraction of the total energy density, which is in this stochastic background. Yeah, this is something that's constrained to be less than 10 to the minus 5 from CMB data, because this is a relativistic degree of freedom that's around the gravitational waves. And then different experiments can probe or will be able to probe this at different frequency ranges. So the ground-based detectors over here will probe these order 100 Hertz regime, and LISA and other space-based missions will probe the millihertz regime, and the pulsar timing arrays are already probing the nanohertz regime and a bit higher. Yeah. So all this data will become available in the future, in 10, 20 years. So here's also Einstein telescope, and there's also a few new proposals which didn't make it onto this plot. There's also astrophysical backgrounds, which eventually we will have to deal with. In particular, there is the expectation that supermassive black hole binaries will contribute a stochastic background at very low frequencies. And then compact binary systems, for example, white dwarf binaries, contribute to both reducible and irreducible backgrounds in the LISA band, and also the thing that we have observed in LIGO already, the mergers of black hole binaries and so on. Okay, so this is a very interesting field of observations. So let's dig in. Now, as I said already, I will be focusing now on two types of sources, namely first order phase transitions and scalar field dynamics, in particular axions, after inflation. So I will not consider the case that the gravitational waves which might be sourced during inflation, which is again also a very interesting thing to study, and also the cosmic strings, very interesting. Okay, so very briefly, the story about gravitational waves and phase transitions. So, well, here is a schematic picture of something like the Higgs potential today. So we have a minimum, which is not at the origin, and this breaks the symmetry. And this gives the gauge bosons a mass, for example. And if you study the system at high temperature, so in the early universe, you see that the symmetry is restored. The origin of the potential moves back. The minimum of the potential moves back to the origin. Okay. So clearly there is a phase transition from unbroken symmetry in the early universe to broken symmetry today. Now the thing gets interesting if there is a barrier between the two phases at around the critical temperature, so that when the second minimum develops and starts to become deeper, the field is still stuck here. In that case, the symmetry will be broken through a first order phase transition, and this is what sources the gravitational waves. And in particular, the energy that is freed up here between, this is really the potential energy that's in the wrong vacuum that is partially converted into gravitational wave, into gravitational radiation. Now, the phase transitions that we expect happened in the standard model are not first order. Yeah, so neither the QCD transition nor the electroweak phase transition. However, simple extensions of the standard model are known to feature first order phase transitions. So if we believe that the standard model is not the end of the story, and I think there is a good reason to do so because dark matter, baryogenesis, and so on, then there's also hope that we could observe such a signal in the future. I will here. Among the sources that people study, new physics models are, for example, modified Higgs sectors, theories with additional scalars, which may or may not be connected to the Higgs. And what's also very interesting are potential connections to baryogenesis and or to dark matter. Here I will focus for now only on the case of hidden sectors, because what I find in addition interesting there is if there's a phase transition in a hidden sector and we observe the gravitational waves, this might be the only way to see those, to get any evidence about this hidden sector if it's completely secluded from us. Yeah, gravity always works. Okay, so something that we did here a few years ago, so this should probably be updated, is to see what kind of what region of parameter space the various experiments would be able to probe for two different scenarios, which are so-called a runaway transition and non-runaway bubbles. This is probably the more realistic scenario. And what you have on the x-axis is the temperature. So this is something is kind of the new physics scale. So you see, for example, here that Lisa will be probing TeV scale new physics, also down to the electroweak scale. Yeah, so this is why Lisa is a very interesting experiment, also from a particle physics perspective. It's because it will probe a region where we're kind of reaching the end of our understanding of the standard model. We still don't know if there are additional terms in the Higgs potential that might modify its behavior, or whether there are additional fields that could change the dynamics and make the phase transition first order, for example. Yeah, what's also very interesting is that these pulsar timing array experiments, nanograph in green, EPTA in turquoise, this is actual data. So this region of parameter space is excluded already. And you see that the upcoming SKA will be able to improve those limits by quite a bit. So here we're probing region of parameter space, which corresponds to phase transitions at MEV scales, so very light new physics. And that, of course, immediately drives you into a hidden sector, because we're quite sure that there is the standard model is not modified at these low scales. Yeah, the parameter on the y-axis is kind of is the inverse time scale of the transition. So this is a very important parameter that determines the magnitude of the signal. So the longer the phase transition lasts, the larger the signal. And of course, if the signal is larger, then it's more detectable. Okay, but this is not so important right now. Okay, so if we look a bit closer at these pulsar timing array region, yeah, so here's the, I didn't update this. So here's the GeV scale, and here's MEV. The question you immediately ask is whether such a phase transition at such a low scale, whether this can be consistent with cosmology. And not only whether it can be consistent with cosmology, but also whether a large gravitational wave signal can be consistent with cosmology. And the problem is the following. If you want to have a phase transition that gives an observable gravitational wave signal at a temperature at or below the BBN scale, yeah, on the one hand, you want to have a lot of energy in this sector that undergoes the phase transition to have a large signal, yeah, because this is your energy budget, the potential difference. On the other hand, we have quite strong constraints on how much energy there is at those times because of the Big Bang nucleosynthesis and CMB observations and the indirect measurement of the neutrino temperature through N effective. Yeah, so it becomes very delicate to find models that work without, so that give you an observable signal without upsetting your early universe cosmology. Yeah, so this was one of the things that we studied in this paper, and one easy way out is to make any kind of model viable is to reduce its temperature relative to the photon temperature. Yeah. However, if you do that, you also suppress the signal. Okay, so you want to reduce the temperature as little as possible. And what we show here in this relatively simple plot is how many relativistic degrees of freedom you can have below BBN for a given temperature ratio. Of course, you can have very little. Essentially, you can't even have a full degree of freedom if its abundance is not suppressed by a smaller temperature. Okay, now, so taking those constraints into account, we again ask the question, about whether SKA would be able to observe actual signals from realistic models, so models that at least in principle could be made consistent with cosmology. And this is now what you see in this figure here. So here's essentially, we studied a bunch of toy models. So here's the example of a Higgs dark photon, where you have the VEF on the x-axis and the temperature ratio on the y-axis. And the green region is consistent with cosmology. So a temperature ratio of 1 is inconsistent, except in the gray region, it's consistent again, because there the nucleation temperature is above the BBN scale. So we don't know, it might be, we might be able to get rid of the degrees of freedom before BBN starts. Okay, of course, so here, of course, there's a transition regime. So what we found is that SKA will be able to probe some of the viable parameter space, but a lot of the region that we showed before is already in conflict with cosmology. Okay, now, why do I mention this? One of the reasons I find this quite interesting right now is that the nanograph experiment saw something. Yeah. So what they observe pulsars and they check whether there is any kind of irregularities in the arrival times of the pulsar signals, and they can use this to put a constraint on the amount of gravitational wave radiation that passes between us and the pulsars. And they're starting to see a non-trivial excess. Yeah, so they see a very low frequencies. Yeah, they see a signal. They see something. They cannot yet say that what they see is gravitational waves, because they don't have full evidence that it's quadrupole radiation. Yeah, so quadrupole, you would expect that the signal should follow the blue line here. If it's a monopole, so not gravitational waves, but some other kind of noise, you would be up here. So yeah, we need to wait for more data. But it's still quite interesting that they might be seeing the first hint of a stochastic gravitational wave background, either from astrophysical sources or from these supermassive binary black holes. Now, we check. So this is again the signal that they see, these gray blobs. And we check that this can also easily be fit with broken power law signals, such as the one you expect from phase transitions. So the dotted line and the dashed line for the two types of phase transitions. And also something that I will talk about in a few minutes. This is what we call audible axion. So both these, all of these scenarios could explain this observation in terms of gravitational waves coming from new physics. Yeah, so that's quite interesting. And we could also do a parameter fit. Yeah, so to determine in particular the phase transition temperature and the strength of the phase transition that would be needed to obtain the signal. And what we found is that, as expected, because this is pulsar timing arrays, the best fit are phase transitions with temperatures in the few MeV range. Yeah. So very light new physics, probably a hidden sector, and you would again have to explain why you're not inconsistent with cosmology. Yeah. So in principle, this signal could be explained using a phase transition, but I think some non-trivial model building would be in order to actually show that viable models exist, and also maybe there are some non-trivial other consequences that could make these observable. Okay. I didn't check my time, but I think I will need a few more minutes, so I hope that's fine. So let me tell you about the axion story that I showed you already. Now, the scenario we consider for the axion is an axion phi here. So a particle with a shift symmetric potential coupled to a dark photon. So this is this x mu tilde. And the motivation to consider such a scenario is, well, there are a variety of motivations. For example, this can increase the viable parameter space of axion dark matter scenarios. This can be used to produce dark photon dark matter. And also in principle, in string theory, this is kind of what you get from compactifications. You get many axions and they couple to all sorts of U1 gauge fields. Yeah, so this is in some sense a very motivated extension of the standard model. Of course, whether it's there in the particular region of parameter space you're interested in is a different question. Now, you're probably, or most of you are probably familiar with the dynamics such a scenario undergoes. Namely, if the axion is initially displaced in its potential, it will start to oscillate when the Hubble rate has dropped to order of the mass. Yeah. And there will be a certain amount of energy density in that in the axion field at that time, which is given by essentially the decay constant F divided by the Planck scale. Okay. And this is what is at the source of the axion misalignment mechanism to get axion dark matter, for example. Now, what happens if the axion is also coupled to a dark photon is that you induce tachyonic instability in the dark photon equation of motion. Yeah, because there is a term here in the equation of specific momentum modes, so momentum k here, that's proportional to the axion velocity, so phi dash. Yeah, so whenever the axion rolls, there's a term here that gives you a negative mass squared, which means you have an imaginary frequency, which means that one of your modes grows exponentially, or at a certain range of momentum modes start to grow exponentially. Now, what this does is, well, you start out with your universe with the dark photon essentially in the vacuum, which means, because this is a quantum theory, you have quantum fluctuations, yeah, so small anisotropies, and some of these anisotropies, those that go tachyonic, will start to grow exponentially, which means that suddenly, after the axion has started to roll, you will have these very large macroscopic fluctuations, so large anisotropies, and therefore a source for gravitational waves. And in particular, since you're only pumping one helicity of dark photons because of this minus and plus sign here, this sources a chiral gravitational wave background. Okay. So you see here on the left, this is the spectrum of dark photons, and on the right, this is the corresponding gravitational wave spectrum that comes in this scenario. So this is something that's also has been studied in the context of axion inflation, but here we're really looking at an axion field that is around after inflation, so during the radiation-dominated era, and therefore the signal is not diluted by inflation. That's why this could be observable. So we checked what region of axion parameter space would be testable by future gravitational wave experiments. And this is mainly the parameter region at the bottom of this mass over inverse decay constant plot. And the reason is that the energy budget, so the energy in the axion initially, is larger if the decay constant is larger. So the gravitational wave signal scales as f over m Planck to the fourth power. And the region down here could be probed by gravitational waves in the future. And this is quite interesting because it's a region which typically is very difficult to probe. Yeah, all the laboratory probes usually work at larger couplings. Okay. Again, we also did a fit of this model to the nanograph signal. And you see again here that we can explain the signal. The fit is not quite as good as for the phase transition, but again, this is very early data. What I find interesting again is that here the region we can already constrain the mass to essentially within a factor of 2 or 3 here, yeah, between 10 to the minus 13 and 2 times 10 to the minus 13 EV. So this very rough data from nanograph already puts a quite strong constraint on this audible axion parameter space, and it also excludes the region of parameter space up here. Yeah, this is already competitive with the constraint coming from the effective degrees of freedom. Okay, so this is, it's one of the first, it's the first such signal, and it already, if it's manifest, it will already tell us a lot about possible new physics, and also already exclude regions of parameter space, which would over-predict a signal there. The same is also true for phase transition. Anything which predicts a larger signal in the nanograph range is excluded already. Okay, I have 2 more slides mentioning some recent results. So what I showed you before, the gravitational wave signal was obtained using some a simple numerical computation where we neglected the back reaction of the dark photons into axions. And once we take this into account, we got a slight modification to the gravitational wave signal. More importantly, also it changes the prediction for the axion relic abundance quite a bit. So this means one has to do more model building to have a viable model. Yeah, so you can look at the results in our paper. And we also studied a scenario where the relaxion is coupled to a dark photon. And there it's necessary to make sure that the field stays frozen after reheating. And we showed that also a region of parameter space in those models. Well, in general, again, the same mechanism applies. So gravitational waves are produced and they could probe a region of parameter space in those models, which is still viable. So which has not yet been probed by other experiments, such as fifth force experiments and so on. This is something that was presented in more detail by Eric on Tuesday. So you can look at his slides if you're interested. One of the things that's upcoming is that we also consider the case where instead of using the potential energy of the axion, we consider the case where the axion has a large initial velocity. And in that case, we get a detectable signal also for smaller axion decay constants, for example, something like 10 to the 13 GeV. Yeah. And then, yeah, so something you can look forward to, something that's also been looked at to some extent in this paper here, down here already. And with that, I think I should come to my conclusions. So gravitational waves offer a unique window into the early universe, and we can hope to observe gravitational waves from a strong electroweak phase transition. This could be the first and maybe even the only way to obtain signals from a hidden sector. It might be a new way to probe axions and axion-like particles. And I think there's lots of room for new ideas in this field. So yeah, think about it. Thank you for your attention.
Yeah, thank you, Pedro, for the very nice talk. Any questions? Yeah, comment. I don't see any. Since the Pedro session will start in roughly around 9 minutes, maybe I think it's time to stop the session here. Yeah.
Okay, thank you.
Thank you, Pedro, and
bye-bye.
Other speakers in this session. Thank you. See you around. Bye-bye.